this video, I'm going to continue the discussion around impact and talk about what happens or how we analyze the situation when the line of impact does not necessarily correspond with the direction of the velocity vectors of the two objects coming into contact. So what this refers to then is the situation of oblique contact. And to kind of give a drawing or graphically represent what I'm talking about, we have two balls, and we'll say that this one's traveling with a velocity vector that looks like this, and this one's traveling with a velocity vector that looks like that. And we can tell that the line of these velocity vectors means that there's an intersection point, so they will make contact. So when that occurs, and these velocity vectors are still pointing in this direction, we have a contact that looks like this. And if you recall the line of impact that we discussed before, that is still present. However, the line of impact looks something like this. And this line of impact is perpendicular to the surfaces of those balls at that point where they're making contact. So it is representing a normal to that curve at that point. When this occurs, then we have to imagine, what's going to happen. These two balls are going to come into contact, and then they're going to bounce away from each other and kind of continue on their line of action. Now, something that's useful for analyzing this is to think about, well, what is conserved when we make this analysis. And the one thing we can realize is, okay, these two balls are heading this direction, they're going to contact, and then they're going to head in the opposite direction. However, we can quickly realize that if we go ahead and define our coordinate system to align with this line of impact as well as a line perpendicular to it, and I'm going to call this coordinate system a tangential normal coordinate system, then what we can quickly realize is that velocity is going to be preserved in the tangential direction while changing direction in the normal component. So if we break apart our velocity vectors into these tangential and normal components, that gives us a little bit more information about what is going on. And we can go ahead and write that the velocity before and the velocity after for particle A are going to be equal, and the same is going to be true for particle B. So this is really useful information, and it'll help us as we go ahead and try to figure out what's going on in the system. The next equation that I can go ahead and write is to start thinking about what's happening then in the normal direction. Well, in the normal direction, we have still the conservation of momentum that we can take into account. So I'm going to write VA normal 1 and the momentum of particle B. Forgot my A over here. And this is representing for us momentum conservation, or the conservation of momentum. And realizing, though, that we're only talking about the normal direction components in this case. Now, what we would end up finding here is we may have too many unknowns to be able to solve this problem, just like we did in linear impact. But we also can be thinking about the coefficient of restitution as an additional equation that gives us more information. Now, the coefficient of restitution in this case is going to be, again, basically purely involving the normal component of this impact rather than the tangential direction. So the velocity loss due to that restitution will primarily be in the normal direction. So I'm going to go ahead and write another equation taking that into account, and that is rearranging from what we saw before a little bit. To get an equation that looks like this, and making the note that this is coming from the coefficient of restitution. Okay, so we have these four equations now, which we can see here. We have equation 1, 2, let's go ahead and number them, 2, 3, and 4. And we have 4 unknowns. And those are basically all the components of the velocity of particle A and particle B in the post-collision time step. So we get those 4 unknowns, but we have four equations, and that means we can go ahead and solve that system of equations and come up with a solution. So by breaking the velocity into these tangential and normal components, we've introduced additional variables, introduced additional unknowns, but at the same time, we've also introduced additional equations that we can use to solve for those things and more information. So we can use this to analyze pretty much any impact, whether the particles are traveling along the line of impact or they're traveling in making an oblique contact where they are not traveling along that same line of impact. All right, thank you.